All right. So I hope we are ready to get started. I have a slightly different setup today. I changed my headset, so the audio setting is changed a little bit. I'm using my cordless mic that I used in class because my other headset, is now somewhere else. So if the audio is not good, for any reason, just let me know. Good day, Nick. So let me know if there's a problem with that. I'm also planning to use the tablet today, um, and there are a few settings related to that I need to make sure is gonna work. Looks like the setting is good so far. Right, I think we are almost ready to go. That well, we still got a minute or so to before we get started. So, do we have any questions? Question? Right. Gonna take me a little bit of time to get used to having my keyboard actually to all the way to the right hand side because my tablet PC is actually where the keyboard used to be. And that's because my cord is only so long I cannot put the tablet on the other side, or maybe just barely I can. Just gonna arrange things a little bit on this side. Right. So the first thing we're going to do today is to take a look at the program that you need to turn in, at 5:30. I go to assignment or lab first, and then I'll go ahead and give you the solution of that particular lab. Um, Not sure how many people were able to finish the assignment. Hoping most of you at least get started with that because, or get a good general idea of how to get it to work. I just discovered one potential issue. My PC is heating up a little bit because the fan, well, it should still work. Uh-oh. Screen just went away because okay. Back and enable it. As I said a little bit earlier, I was messing around with settings a little bit and monitor is back, but I want because I'm only using the tablet screen to do the stuff that the tablet does. My main monitor is still going to be the main display. But, all right, so I got everything back to where it's. We'll go ahead and get started with the lecture. All right, so let me go through the text comment, starting with small testable bits. Hmm. Well, that's the thing about programming. With so this is responding to Alex's comment. It's a very small bug can lead to a lot of serious problems down the line, and there's no way anyone can tell when to um, uh, how long it's going to take to finish programming. So that's kind of the one of the main issues. Um, I'm just looking at the YouTube stream. It looks like it's still working okay because I got a warning from my own computer saying that streaming, maybe the quality of streaming may be limited because my process is getting a little bit hot, so it has to throttle its clock. That's because the usual fan that I use to help cool the laptop computer is no longer next to the computer, so might be causing a little bit of a overheating issue. So go ahead and see. I'm trying to redirect airflow to help cool down the computer a little bit. All right. All right. So what we'll do is we're going to take a look at the assignment. The first thing is to confirm that it is not within the time anymore. People should have turned in already. And then we'll go ahead and look at the code because I want to work on exactly the same code. Question number 3, code. And this is the subroutine. This is main. And go ahead and text terminal. So go ahead and see if I can kind of overlay side by side, at least for the first part. I know you cannot see the other half of the terminal, but you only need to part of it. All right. So before I get started with this, I want to comment on how important this homework assignment is. Not so much the number of points, because as most of you probably realize, the number of points for this much work is not really a whole lot. Okay, so it's not because of the point values much, but this homework assignment also helps you understand the concepts that we have been talking about all along. Okay, I know some of you may have made a bug that is just a careless mistake, and it took you a long time to find the source of the problem, and even that really is studying. I mean, understanding how a particular kind of bug can lead to what kind of symptom is studying in this class, because we want to understand how the stack is utilized, or in this case, if the stack is not properly utilized, okay, if we do not adjust the stack pointer correctly, what is going to happen? Okay, so all of that is actually studying. Um, so if you cannot manage to finish this program, but in the process you're learning, you're reinforcing a lot of the concepts that we have talked about in class, it is still a very good exercise. Okay, the worst thing that can possibly happen with this homework assignment is somebody not even going to give it an attempt or give it a try because it's not worth the points. Okay, to me, that really is the worst case. Okay, anyone who puts in the time to try to get it done, is going to get some benefits out of it. Okay, so having said that, I am going to write this code. So just call it f.ttasm, and then we'll go ahead and do the usual stuff. Okay, so we have no op and jmpi to main. Here we have main alt instruction. Then I'll go back and look at function f. So here is function f with entry point of just a label, f. And the first thing we need to do is to define some labels. Okay, now if you don't want to define labels and you say I know how to get to items on the stack, that's fine too. Okay, but personally I prefer to have labels. So parameter end of f is fn, okay, with an underscore, and that is located at 1 byte after the return address. So return address basically at a displacement of 0 from where the stack pointer points to. So f underscore n is going to be f underscore address 1. plus because it's multiplied beyond that. So as far as parameters are concerned, it's not that big of a deal. We only got one in this case. And now we can go ahead and write the subroutine. The first thing we need to do is compare n with 2, and depending on whether n is less than 2 or not, we go to either the then branch or the else branch. Go ahead and get to the value of n first. So the typical code to do this is to LDI with one of the 3 available registers, which is A, B, or C, point with f underscore return address, which is the displacement from where the stack pointer points to not return address, we n fn, and then you have to remember to add d to a, because otherwise register A only contains the displacement, which is not really an address of any kind. It is really just a displacement. So now, at this point, register A is the address of parameter n in this particular subroutine. But we don't really want the address. We want the actual value, basically LD instruction. So LDAA work. So in this case, A is now the actual value of n. Now we can actually do the comparison. Comparing against 2, there's no quick and easy way to do it. So it's just just have to load as a constant register B, and then so to compare, we have 2 directions. We can compare AB, which is looking at the subtraction of B from A, or we can do it the other way. Okay, so in this case, we are trying to determine whether n is greater than or equal to 2, because if that is the case, we want to go to the else case. So if we're looking for the condition of n being greater than or equal to 2, then the comparison should go the opposite direction. So we do a CMPA. In other words, we are basically performing 2 minus n in this case. And then we try to determine whether 2 is less than n or not. Okay, because if 2 is less than n or equal to n, we go to the else case. I'm trying to preserve the structure of the original code as much as possible. So this is not the only way to do it, but one of the 2 ways to do it. So we use a JZI else value. Basically, this is saying, if n does equal to 2, then we go to the else. Okay. So that's one way to get to the else. And then the other way to get to the else is when n is greater than 2 or when 2 is less than n. Okay. So we have to choose between JCI versus JLI, because both are jump if quote unquote less than, but one is for unsigned comparison and the other one is for signed comparison. So for unsigned comparison, because the C code states quite clearly that we are dealing with unsigned values, so for unsigned we have to use JCI. So JCI would also go to else value. If in this case, if n is greater than 2 or if less than n, go to else as well. Okay, so if we end up here, then we have the then case, and you can see how the if, else, then, while, all of those are highlighted, even if they are appearing in comments. That's exactly how the syntax highlighting rules are set up, so that these specific keywords are highlighted even though they're in comments. So in the then case, okay, we just have to say, hey, register A, which is the register that I use to return the value, already has n in it already. Okay, so I here and say A already has return value n. So there's nothing I need to do here. I can now JMPI f underscore return code. Okay, somewhere down here. F underscore return is going to be defined here. We'll deal with it later. Okay. And if I go back over here, now I can define else value as label to basically handle the case of, we need to do the recursive call at this point. So do we have any questions up to this point? Are there any questions anyone want to ask before we move on? Okay, Angel is typing. So is Thomas. Okay, so Thomas has a question. Do we have to use CMP, or would subtracting 2 from n and using JSI also work? Okay, so let's answer Thomas' question first. So the answer is no. Technically, the answer is no. JSI will not work correctly when we have unsigned values being compared. Now, that being said, the case when JSI will start not to work is when n is 128 or more. Now, there's not enough stack space to practically handle the cases of the Fibonacci sequence number of 128 or more. So practically speaking, I cannot test, or I cannot give you a test case where it will make a difference. But in terms of correctly using the flag, we should use the JCI and not JSI or JLI. So that is for Thomas's question. Moving on to, okay, you're welcome. Moving on to Dom. Can we use JSI after the CMP? Same thing. Okay, so we should use JCI and not JSI. JSI is typically not really used a lot because in a comparison, we don't want to use JSI or JOI because we have JLI to combine the two into one. So we remember that the sign flag is not reliable in the case of overflow, but the overflow flag by itself obviously is not going to be very helpful either. So neither is appropriate after a compare. It is only JLI that makes sense after a compare if the values being compared are signed values. So moving on to Angel's question, how would this code differ? Okay, so we have the label. Okay, so we don't want to change D because changing register D is a big no-no. Because the way we're changing the D in Angel's example, I hope all of you are looking at the text channel. So LDI D comma N is going to change register D. It's going to change the stack pointer. So if we do that, we are irreversibly damaging the stack pointer. There's no way to recover the stack pointer after that. Okay, now increment and decrement obviously would change the stack pointer too. But if I decrement the stack pointer, I can always recover by incrementing, okay, by the same amount. So it's definitely a no-no if to change the stack pointer. And it would also not get the correct value into register D either. And the reason is the moment we change register D to N, which is the offset to where the variable, to where the parameter is on the stack, we just lost the stack pointer. Okay, so there's no way to find out exactly where N really is on the stack anymore because the very first instruction is destroying the stack pointer. So we don't want to do it that way either. Right, so getting back to the code, so getting to the else value. Okay, so the else value says the first thing we want to do is to subtract 1 from N and then pass it as a parameter and call F, and then we want to pass N minus 2, basically the same thing. So we got a few options here. We can, I'll go with the most obvious way to do this first. Okay, so at this point, register A is still the value of N, so I'm not going to go get it again just because, hey, we just put it into register A for the purposes of comparing, so we know register A still has N at this point. So what we'll do is we are just going to move forward and say, let's push N minus 1 on the stack. So to do that, we just have to decrement A. So the register A is now n minus 1, and then we have to push it on the stack, which means we want to decrement D and then ST A. So this is going to push n minus 1 stack. Then we go through the usual stuff to call, okay, which is decrement D, LDI, A with dot 5 plus. And the syntax highlighting is actually correct in this case. This is legitimate code. For why is okay? Something for me to fix. Okay, so LDIA.5 plus is loading the return address into register A, and then we have to store this onto the stack as well, wherever the stack point is pointing to. This is pushing the return address on the stack. And then we can just go ahead and do a JMPI to the subroutine that we are calling, but we are calling really just F itself, so JMPI to F is fine. When this invocation of F is done, we are coming back to the point where the cursor is. So at this point, we really should deallocate the argument. Okay, deallocate the argument means we just increment D. Okay, so we are allocating argument n minus 1 from the stack. Okay, so now the stack is balanced again. Okay, the stack is back to where the stack pointer is getting back to where it was at the entry point of subroutine. In other words, the stack point is once again pointing to n. Now, the other question that someone may have is, well, can't we just pop the argument back into register A or some other registers, decrement it one more time, and then push it back on the stack instead of going back to try to get n again? Okay. The answer is we don't want to do that because there's no telling what the subroutine has been doing with the parameter. Okay, so we don't want to make the assumption that the argument that we push on the stack remains exactly the same when the subroutine is done. Okay, so we just basically say, I have no idea what the subroutine has been doing with the argument, so I'm going to assume I cannot trust the argument is the same on the stack. So I just have to go through the same exercise to load it back into register, and this time decrement it twice before we push it on the stack. So we basically go through the same motion, which is LDIA F underscore n, and then I think I know why the dot 5 plus is not working. I think it has to do with the dot. Dot is not recognized as one of the things that can appear in a postfix notation. So I'll go ahead and fix that a little bit, but before we do that, we'll finish this. So add AD to get to the address of parameter n, and then we have to do a LDAA. So the A is now the actual value of parameter n, and then we have to decrement it twice so that by the time we get here, A is now n2. Then we can push it on the stack. Means we decrement the stack pointer again, and then we push it on the stack. Now there's one little problem here. Okay, talk about what that problem is. By doing all of this stuff here, I have just destroyed register A. Okay, starting here, I have destroyed the value of that I have stored in register A, actually the one before, the LDI instruction here. So that is really bad because register A right now actually has the value of the return value of calling F the first time. In other words, F of n minus 1's return value is in register A at this point. Once I destroy it, it's gone. Okay, there's no way to recover that. Okay, so it is probably a good idea to put it push it on the stack first. Okay, so to push that on the stack, that means I have to decrement D again, and then do a STA. Okay, so this is for pushing F of n minus 1 stack so that we can retrieve it later. Now, at this point, most people would see that, hey, you have an increment followed immediately by a decrement of the same register, and that is true. Okay, so what we can do is we can now comment out both of them. Okay, I'm not deleting both of them because technically speaking, we are incrementing the stack pointer to deallocate the argument, and then decrement again to allocate the space to push the return value of f of n minus 1. So technically speaking, we are doing the two, except they cancel out each other. Okay, so we don't have to do it, okay, because they just cancel out each other. But in terms of conceptually speaking, we should do these two instructions. But that's a problem because by the time we get here, the label fn is no longer correct because we have now one more item on the stack. So the offset from where the stack pointer points to parameter n is wrong if I just use the label fn, because I have to now remember that there's one extra byte on the stack between where the stack pointer points to and where parameter n is located. That one extra byte on the stack is the return value of f of n minus 1. So this trick, I think I have shown you guys before when I use the 5, 7, and 12 example. Okay, so that's really kind of an important point to make here. Okay, and then the rest of this is going to be about the same. So over here, we are pushing n minus 2 on the stack, which is the parameter, the argument that we want to push for the second call of f. And then we decrement d again, LDI a 5 plus. So this time we are loading the return address again, and then we have to push it on the stack, sta, and then another JMPI to f. So this is the second call to f. Do we have any questions up to this point? There are no questions. Okay. If you want me to slow down and just kind of so that you have a chance to read the code and absorb it, you'll let me know because I can certainly slow down a little bit here. So when we return from the second call, okay, once again, we have to deallocate the argument from the stack. So that's just increment d, okay? So this time we are definitely deallocating n minus 2 from the stack, okay? And then the stack pointer is now going back to point to the return value of f of n minus 1, okay? So we're gonna pop that now, which means we're gonna do a LD instruction, and we have to put it into a register something other than register A, because at this point register A has the return value of f of n minus 2. So we don't want to destroy register A. We can use register B or register C at this point. So we'll put it into register B. Then we do another increment D. This is for deallocating f of n minus 1 from the stack. But we also want to kind of make it clear that register B at this point is the return value of f of n minus 1. Okay, and register A is the return value of f of n minus 2. So now we got both values that we want to add. So we just have to have an add instruction. So whenever you use the add instruction, you have to ask, which way am I adding? Am I adding B to A, or am I adding A to B? So in this case, it makes more sense to add B to A because register A is the return register. It's the register that holds the return value. And so why do I want to add A to B and only to have to use CPR copy register later to copy register B back to A? So I might as well just add register B, which is the return value of f of n minus 1, to register A, which currently has the return value of f of n minus 2. Then everything is calculated, should be calculated correctly. And now I can fall through to the label of f return. So when I get to the label f underscore return, the only thing I need to do is really just to return control back to the caller. The return value is already done, okay? That part is already done. I just need to get the return address from the stack, deallocate it, and then jump based on that. So that we know already how to do. Just load B with whatever the stack pointer points to, and then we increment D to deallocate the return address from the stack, and then JMPB to return back to the caller. So are there any questions about this code here? Basically, all this code is what we need to do just for that one line in C code. So he's typing. I'm going to wait a little bit. And the rest of you can use this opportunity to think about, do you have a question that you want me to address at this point? Right. Postfix. So dot 5 plus is dot plus 5, and dot is the address of the instruction where the expression is contained. So in this case, it is the LDI instruction. The LDI instruction has 2 bytes. So the dot is representing the first byte of the LDI instruction. I'm adding 5 to the address of the LDI instruction and then put that into register A. Kevin has a question. Right. Okay. Right. So now we can kind of move on to main. Okay, we got some additional questions. I'm gonna wait a little bit. While we are waiting, might want to just. So we load A with 5. No, register A is not loaded with 5. It is loaded with the address of the LDI instruction plus 5. So this would be more obvious when we get to the assembler, because the assembler can show exactly what is the constant being loaded into register A. And let's see, Thomas has a question. Is it best to use labels for parts of function? I'm assuming what Thomas is asking about is the location to, yeah, the location to return to. I personally do not like to use labels because that is just room for more error. F underscore return needs to be there because I need to have a label to skip to in the if then else control structure. But in terms of dot 5 plus, that's a different thing because that is specifying a return address for calling to a subroutine. Okay, all right, cool. So what I'm doing here is I'm just changing the syntax highlighting rules here. And the rule that I need to change is the one that handles LDI or anything that has an I in it. I know this looks kind of distracting, and it really is. So this is one of those lines I have to allow the use of the dot in it. Allow a dot. If there's one more alternative, which is a backslash bar, specifies an alternative, and it's just a backslash dot here to specify a single dot, because without the backslash to escape it, a dot means it can match anything. And then this one is the actual LDI. It has to be treated the same way. So we have to use a backslash bar before the end of the group. Group is to specify a single dot backslash bar. Alternative. I think those are the only two anything that can have immediate back. Seem to change it, but that may be because it has not reloaded the syntax file. Okay, we'll go to main first. Okay, so we are now getting to main. Main is over here. It has got a local variable, so we need to allocate it and also give it a label. So main underscore x is going to be 0. Okay, I know this looks kind of strange because where's the return address? Don't we want to have a return address? And the answer is no. Main actually has no return address because unlike the implementation in regular C or C++, where main is actually called from libc. Um, in the toy processor, there's no operating system to do a call to main. So main really has no return address. So that makes the local variable in main being pointed to by the stack pointer, basically once it is allocated. So in main, we have to do a decrement d. Okay, this is for allocating local variable x. And then we have to call Fibonacci number or the sequence. And one of you tested it with 7, so that's kind of ambitious. And it ended up working too, so that's great. So let's go ahead and do that. Okay, so with LDI A with 7, we push it on the stack, which decrement D, STA, pushing 7, which is argument stack. And then we decrement D again, LDI A with dot 5 plus, which is address, STA for pushing the return address on the stack. And then we can actually do the call or continue execution in the subroutine, which is JMPI to F. When this is all done, we're going to go back to the point where the cursor is. So we need to increment D, allocate argument 1, and now we can focus on what to do register A, because register A stores the return value. So if I want to be super lazy, I could do something like this, okay, to basically say local variable x is getting f of 7, but I'm not going to do it, okay, because this is based on the assumption that there's only one single local variable on the stack as far as main is concerned. So the moment I try to add more stuff, to the local variables, this is no longer going to work. So I'm not going to do it this way. I'll comment it out. So, and now we're going to do it the proper way. The proper way to do this is to put something into register B. I cannot use register A anymore because register A still has the return value of F. So I cannot, destroy register A at this point. So I'm going to do LDIB with offset, which is main underscore X. Do an add instruction, add BD, so the register B is now the address of X in main. And then at this point, we can do a store. Okay, so we're going to store to where B is pointing to, whatever A contains. So yes, so if you look at this, it's like, hey, register B is really the same thing as register D because we are just adding D to 0, which means register B is really the same thing as register D. But conceptually speaking, making use of a label means I can change main X later on, and this code will continue to work. So that is the important part of this here. And before we get to the hold instruction, we also have to deallocate the local variable, which means we have to increment D one more time. Okay, this is for deallocating local variable X from the stack. Okay, so that should implement main itself. Do we have any questions about this program before I give it a try? The assembler. Okay, question. Right. So if there are no questions at this point, I am going to exit from Vim. And just for curiosity, I want to go back in and see if the syntax highlighting rule changed, fix the problem. And the answer is no, no. Okay. Okay, let me answer Thomas' question first. Would you ever use a variable for passing parameters? Not quite sure what that means. Are you referring to a global variable? Yeah, so the answer is no, because in C and C++ we have the concept of a parameter. So it's much better to pass values using parameters instead of using global variables. But in some other programming languages, such as COBOL and Fortran, parameters, Okay, with COBOL, there's no such thing as parameters. Okay, when you're calling a subroutine, so the only way to pass any information in or out of a subroutine is to make use of global variables. Yeah, I know that's kind of ugly and but that's it's a limitation of the programming language, and there's a kind of a reason for that too. Um, and then the second part of Thomas's question was, but I don't know why, such as fvar. Would you label var? Hmm. Well, if var is a local variable, so okay, so let me go back to this code here. Okay, so I can put 7 into x first and then pass x instead of the constant 7, push that on the stack as the argument. I could do that too. Okay, so I'm not sure whether that is what Thomas was asking. Okay, yeah, so that's perfectly okay. I mean, there's nothing wrong with doing it that way too. Asking. It's important to differentiate between how you make the argument, something that you push on the stack, and who owns the variables involved to calculate the argument versus what is the subroutine that you're calling with that argument. I think it's important to make that differentiation. I'm waiting for Hugh to finish typing. Well, fix my syntax highlighting again. Yes, I am kind of obsessed with that. And all of this stuff here is regular expression. We talked about regular expression a little bit when we talked about doubles and floating point. Okay, so Professor, is there a way to track the stack in C? Because I'm thinking that if we do see the C stack, we could use C stack to do the same CTPASM. Hmm. So let me see if I can understand, see if I understand the question correctly. So from the question, I think the question is asking, can we use register C instead of register D as the stack pointer? Is that what the question is asking? Because in the processor, we are able to see RAM file. Hmm. The processor doesn't quote unquote see the RAM file. The processor can access locations in RAM. So it's not exactly the same thing as a RAM file. The RAM file is an image that gets loaded into RAM, and then the processor, using the address port, can access locations in RAM, either write or read. And then based on the wiring and the configuration of the multiplexers and the demultiplexers, we can basically read the content of RAM into a register, into the program counter, into the instruction register, so on. Meanwhile, I'm going to try to debug text highlighter. Okay. Um, I mean, if we run the processor or the analyzer, we can see how data is stored on the stack. Yes. But for this class, the assumption is register D is the stack pointer. So we just make that convention because it has to be a convention that both the caller and the callee would agree to. Because if only one is using register C and the other one's register D, then we're gonna have a problem because there's no common stack anymore because each piece of code is making a different and incompatible assumption. I think Thomas was typing a bit until Okay, so I think he might have meant with a stack program written in C, we can see how the stack works. Oh, I see. So C is referring to the programming language, not the register. Okay, that was my bad. Okay, all right. Okay, so the thing about a C program is there's no trace analyzer available when you have a program written in C. Um, and that's one of the problems of debugging a C program, because once you once your GDB is past a certain point, there's no way to back up and ask, hey, what was the stack pointer pointing at? No, 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 that's fine, not a problem. But to answer the question is, if a if an architecture has a way to basically log everything the same way that the Logisim can log things into the log file, then yes, the answer is yes, we can trace analyzer. But most processors don't do that because with a complex program, you would be generating a huge amount of trace, just from executing a small program. Um, so, but that being said, okay, that being said, let me show you something over here, and I'm gonna go back to my obsession a little bit later. There is such a thing called a logic analyzer. Okay, so look up a logic analyzer. Okay, and you can look up C80 pod. Okay, okay, so let's click go. Show a picture. Yes. So it shows a picture of a pod to debug certain kinds of processor. 8051 is a certain processor, and this is what we call a pod, which is basically just a kind of like a module, or in today's term, it's kind of like a plug-in. Okay, so it plugs into something that we call a logic analyzer, and a logic analyzer is not a software thing; it is an actual physical instrument, and are actually very inexpensive for logic analyzer. When I was in embedded system industry, a logic analyzer was a used one was about $5,000, and we are talking about 1990 case. So what a logic analyzer is it can you can connect a lot of different uh, parts to it. So what each part really is a bunch of wires that you can plug onto a circuit board to monitor the data bus, the address bus, and so on. So in earlier processors, everything is quote unquote exposed. So the data bus is exposed, the address bus is exposed, RAM cell is actually exposed. So all of those pins are actually exposed. So by using a part like this to electrically connect to those conductors on the circuit board, um, this type of instrument called a logic analyzer is capable of basically logging everything the same way that running Logisim on the command line can log all of the zeros and ones. Okay, and then a specialized program can look at those logs and then figure out what the processor has been doing, just like what the trace analyzer is doing with the log file that we generate from running Logisim on the command line. So the answer is yes. So there are such things in physical world, in certain industries to do the same thing. Um, Basically, it's the analog or physical version of what we do in this class. So I hope this kind of answers that question. Kind of long, but I hope that answers the question. All right, getting back to my session here because I just want to find out why is it working. Oh, I think I know why. Yes, it cost a lot in the past. I don't think they cost nearly as much these days, and for a few reasons. I think that goes here. Alternative odd. Go over here. Same thing. Out. Alternative. I just put the alternative into on grouping. Oh, here. Yay! LDI dot 5 plus marked as an error. Woohoo! Okay. All right. So let's go ahead and test this program. Okay. I still remember what I was supposed to. And we want at tip. What this does is it puts the entire program into the clipboard of the system. So this way, when I get to the assembler, I can just paste it in. Drive. The other thing that's kind of interesting related to use question um, is a lot of processors can be simulated, not using Logisim, but some other more professional simulators. And those simulators or emulators can log uh, the what is happening on the data port, the address port, and so on and so forth. So there are ways to debug a processor um, without um, silicon, without implementing the processor in silicon. So that can also be done. All right, so getting back to our assembler. The embedded system industry particularly use tools like that. Okay. All right. So the first thing we want to do is not so much to load the program in and get it to run, but to explain one thing that I promised that I would explain earlier, because Angel asked a little bit what is the .5 plus. So we'll go ahead and address that question first. The best way to look at it is from the Assemble tab of the spreadsheet. I hid some of the other tabs. They're still around, but they're hidden. But the Assemble tab is particularly helpful, so I'm not hiding that one. So we'll go ahead and look at one here, row 24, which has LDIA .5 plus. So from column W, we can see the address of the LDI instruction is 14. That's the location of the LDI instruction. So what is loading into register A is a 19 because 19 is 14 plus 5. So that's what the .5 plus is doing. Now, if you look at another .5 plus on line 38, it's kind of the same deal, except this time the LDI instruction is at location 23, and it is 28 that got loaded into register A because 28 is 5 past 23 in hexadecimal. So I hope this kind of helps to address the question from Angel earlier. Is that good so far? Okay, I'm assuming it is good. So we'll go to the RAM file and go ahead and download program. So this is the content that we'll put into RAM. For f.csv program. Once we have that, try to run it on. Just gonna repeat the previous command, type the whole. Just have to change the name of the RAM image from test f.csv key, and this time it's going to take a little bit of time because f of 7 actually has quite a bit of work to do, and then plus the processor is clocked down because of a heating issue. So right now my processor is running at 86 to 90 degrees Celsius, so it has to throttle the clock so it doesn't kill itself, in the process. It is running a little bit hot. All right, so we are now getting to the point where we can um, put it back in Trace Analyzer because the log file is done. Go to all right, so port, and it's going to take a little bit longer than you just because CPU is throttling it as quickly as log. Update a bunch of stuff. This trace is a little bit longer than usual, so it's going to take a little bit longer. Plus, the processor is throttling itself, so things are going to run kind of slow today. But the reason why I want to enable the tablet mode is because I want to draw a picture of what is on the stack from the perspective of the subroutine, at least at some point. That picture is not really needed because we have the trace analyzer to actually tell us what is on the stack at any time. But we'll go ahead and take a look also. All right, so we have to go find the end of everything. I keep length somewhere. Summary. Yeah, it's not shown though. The one quick way to do it is to find where's the address of the halt instruction and just for it. You go to the Assemble tab, Assembler, scroll all the way down until we find the halt instruction. And the halt instruction is at location 40 hexadecimal. So we can go back to the trace analyzer now. Just say, go find me location 40 in column A. Highlight. So H, and we want to find 40 decimal. Range is A. Go. There we go. All right. So now we have reached the end, the end of the execution of the program, and we can see how this time it's using up like 4,000 something, rows because each row is representing something got changed in the processor. Okay, it may not be something that is important to us, but something internal to the processor changed. But what we want to know is what is written to local variable x of main, and this is what is written to that location. Okay, I think somebody sent me. I think it's Thomas, right? Used 7 as the test case and got 13 back. I think that is the case. Yes. Okay. So thank you, Thomas. So 0D is the correct answer. Okay, because f of 7. If you look up, just do a Google search on Fibonacci, it'll give you all the values of that sequence. So if you look up Fibonacci and look up the first one, it's actually listed here. This is f of 0, f of 1, f of 2, 3, 4, 5, 6, 7. So f of 7 is supposed to be 13 because it is 5 plus 8. Okay, so the subroutine is actually working fine. Okay, that's one thing that is kind of nice. But then the second question is, how much stack was used in the process. Okay, so that's a different question. In other words, we want to go to the trace analyzer. Okay, there are two ways to answer this question. So the first way is the empirical way, which is really just to utilize the trace analyzer and ask how low did register D go when we ran this program. Okay, that's basically the question is how low did the stack pointer go ran this program. Okay, and there are several ways to answer the question, because you can go from the RAM right column and then you ask what is the lowest location that we wrote to in RAM right. Okay, or you can use column B and ask, okay, if we just look at all the entries of D equals something, what is the lowest value, not counting 0, 0, itself. Okay, so you can use all of those methods to locate the lowest point of the of where the stack pointer points to. Okay, because that will tell you how much uh, how many bytes are actually used on the stack. Okay, so you can do this empirically, but you can also answer that question from a more theoretical perspective. Okay, so let me go back to the editor so I can actually explain that. Or better yet, since I already have the tablet mode on, I'm gonna use that feature. Journal, and now we can use the tablet, which is the reason why I set it up today. So next time I do this, I'm gonna have to have a CPU cooler, underneath my tablet to push all the hot air out as quickly as possible. Because today the processor does run a little hot. Let me. It's running at 90 degrees right now, so almost boiling point. It has been doing this, for since the beginning of the lecture. Okay, so let's go ahead and take a look at what the stack looks like. Okay, so if this is the stack, okay, initially the stack pointer or register D is pointing to location 0, 0, but that 0, 0 is really location 1, 0, 0. We call it location 0, 0 because with only 8 bits, I can only represent the least significant 8 bits of 1, 0, 0. But the actual value I want to represent is the location after FF, which is 1, 0, 0. Okay? The first byte I allocate from the stack, this is at location FF. That's the local variable x of main. Okay? So local variable x of main is using up that byte. Okay? And then the first invocation of f is going to use up 2 additional bytes. Okay, this byte is used in our specific program to store the constant of 7, which is the argument that we pass to the first invocation of f. And then the second or the third byte down from the stack, from the top of the stack, is the return address. So this is the return address back to main. Okay, because that's the first invocation. The first invocation is coming from main, so as a result, it has to go back to main. Okay, so now the question is, when we do this, how far the stack has to go? Okay, so now we have to analyze the subroutine itself. Okay, the subroutine itself has 2 invocations of f. The first one is going to take up 2 bytes. The second one is going to pop this location. It's going to use up 2 bytes in the first one, but then the second one is going to use up 3 bytes because the second one has to use the first byte to save the return value. Then we have the argument, and then we have the return address. So if you look up, and you basically look at all the second call of f, then each invocation is going to take up 3 bytes. Okay, so now the question is, how many of these second invocations are we talking about? So we have to go back to the code to analyze that, because this is corresponding to f of n minus 2. Okay, so when we are calling f of n minus 2, it's going to use up 3 bytes. Okay, f of n minus 1 is only going to use up 2 bytes, but since we want to find out what is the maximum amount of stack space it's going to use, so it's going to be f of n minus 2. Now, if you want to analyze this kind of using a more empirical way, you can kind of look at this as say, okay, when we try to compute f of 5 from the first invocation, it's going to take up 3 bytes. Okay, so that means n equals to 5. So that means the second time it's going to use up 3 bytes is going to be when n equals to 5 and we're trying to figure out f of 3. Okay, and when f equals to 3, then the next time then we have to ask, is there a next time it's going to use up 3 bytes? So when n equals to 3, it's going to go for the recursive call again, because it's only when n is less than 2 that we do not do any further recursion. So when n is 3, we definitely want to do the recursion. So when n is 3, then n minus 2 is going to be again here, n minus 2 is going to be f of 1. Okay, so f of 1 is going to use up 3 additional bytes on the stack, but f of 1 does not do any further recursion. So that means by the time we get to f of 1, it would just use, it's not going to use any additional bytes. So that means this should tell us, how much RAM is going to use, or how much of the stack space is going to use when we execute this program. So we'll go ahead and do some counting here. So we have 1, 2, 3, and then 9 over here. So this tells us that we might be using up to 12 bytes as we execute the program. So now we have to find out, okay, what is 12? What is 100 minus 12 in hexadecimal? So we say 100, okay, 0x, which is hexadecimal, minus 0x00c, because c is 12 in hexadecimal. So we have basically f4 in this case. So the stack pointer should not go below f4 if I am analyzing the program correctly. Okay. Let me, that makes, no, actually it doesn't make sense, because the first one, the -1, that one is actually going to go deeper than the second. So I think it went below FC. I did this calculation is actually not. Okay, but we can confirm that it is actually not correct by looking back to. Because we can look up column D, highlight column D, control H, and then we look for D equals to, first of all, FC. Pretty sure we got to F. Go. And we can definitely tell that it went below that. So the question is, how low did it go? Goes back and forth a little bit. A. Back to. Because the reason why I made that mistake is, the first call, which is just dealing with f of n minus 1, even though each invocation is only taking up 2 bytes, there are more invocations than the other. Okay, so let me go back to slide over here. Okay, so if you look at the first call, f of 6 is going to be here, and then f of 5 is going to be here, right? And then there's f of 4, 3, 2. So f of 2 still needs to call recursively call one more time to get down to 1. So we are looking at 6. Excluding these 3 bytes, okay? Excluding those 3 bytes, we are looking at 6 times 2 bytes, which is 12 bytes. So altogether, we should be using 15 bytes, which means the stack pointer should go as low as f1 according to this calculation. So let's go ahead and check if the case. We want to look at d equals to f1. and you look at this. Okay, this is still pretty early in the trace, so it doesn't seem like that is the case, but it's misleading because this might be the deepest part that we reach in the entire algorithm. So look for d equals f2, so it's going back up again. We are deallocating stuff, reallocating back to f1, f0. Okay, it went even further. Yep, so from that point it went back up again. So I just missed it by 1, which has to do with okay, I know exactly why it went 1 byte deeper than I thought it did, because I forgot. What I forgot is when it got to f of 2, which only takes up 2 bytes, but the first one, which is f of 1, takes up another 2 bytes, which I accounted for over here. But the second one is when it needs to compute f of 0, which takes up 3 bytes. So that is the 1 extra byte that I did not account for, because f of 1 is only taking up 2 bytes because it's the first of the 2 calls to f, the first of the 2 recursive calls in f. But the second recursive call is going to take up 3 bytes. So that is the one that I did not account for. That's why it chew up 1 more byte to handle that one. Okay, so I think everything seems to be accounted for. So the lowest location in this case is f0. Let's go back here and just confirm that. So we'll go look for d equals to f0. Found it. And we just have to ask, does it get any lower than that? Okay, did it get to EF? Question. And it doesn't match. So F0 is indeed the last one. Phew. Okay, so are there any questions about what I just explained regarding the analysis of the algorithm to figure out, how low did it go? How low did the stack pointer go as we perform these recursion? No questions, or do we need just a little bit of time to formulate the question? No questions? Excellent. All right. So I'm assuming the class is okay with this as well. Okay, so I will post the code over here right away before I forget. Okay, so instead of waiting until the end of the class, I might as well just now. I call this f dot program. Now that is posted online, I'm gonna pin it too, so this way you don't have to scroll through all the messages on that link. All right, so if you're monitoring the Discord side, you should be able to see uh, the file as an attachment. And I strongly recommend everybody, okay, unless you get everything up and running yourself, to take a look at this program and at least understand how it works, particularly what is the agreement between the caller and the callee, the subroutine being called, and how the stack is being utilized, in this particular program. So every single instruction is important, as far as understanding why it is there, what does it do in the program. Okay, so are we okay and done with the Fibonacci program at this point? Like we do not have any questions. All right. I'm looking at the time. We got about 10 minutes before the end of the lecture. So what I want to do at this point is kind of go back to structures, okay? And so let's see if that program is due. Uh, so the program is still here. It is list.c. .c is one of the programs. The one is allocation. So this is list.c, which is constructing what we call a free list. No, this is not constructing a free list. This one is traversing a list to find the sum of all the value members of all the nodes in that linked list. And the linked list itself is created just by creating the global variables initialized in this particular manner. So this is one of the programs that we worked on last Thursday. And I think the program in assembly has a similar name. It is list.tasm. The program, the assembly language program corresponding to the same C program. So does anyone have any questions about that particular discussion? About list.c, the implementation, and the TTPASM version of the same code, but implemented in assembly. Do we have any questions about this one? Okay, Angel is typing, so I'm going to wait a little bit. Okay, so the question is, the original purpose is to implement a linked list, basically, um, data structure, no manipulation for it or use for it yet. Not quite fully understanding what the question is asking. Are we asking, are we utilizing the program or not? Is that kind of what the question is asking? And since I have the tablet up and running, okay, this is actually a very good opportunity to explain this program, but using a picture instead of just looking at memory locations. So I'm going to wait for Angel's question, but as I wait, I'm going to look at the C program again. But this time we'll take a look at a pictorial representation of how nodes 1, 2, and 3 relate to each other in terms of picture. Journal here and take a look at a pictorial representation. I have to put items on the screen so that we can see both journal and also the text of the program. All right, so is just wanted to make sure if we are building the data structure. So in this case, we are building the data structure using initialized structures. So when you look at this part here, that really is just initialized variables as global variables. But what the data is going to look like, okay, if I want to represent it graphically, it's going to be something like this. Okay, so node one is basically a block of memory somewhere, okay, and it has two parts, right? It has got the first part, which is the value, and the next part is the next pointer. So I'm just going to use v and n respectively to refer to those two members. So in this case, for variable node 1, so when we say node 1, it is referring to the whole thing. It's referring to both members. But in this case, value is 5, or at least that's how it's initialized, and then the pointer to the next item is null, which is basically the constant of 0. Okay, and when we look at node 2, okay, so these 2 bytes, which also has member v and member n for the value and the next pointer, this is our node 2. So the value of node 2 is pretty easy to understand. It is just 23. But the pointer, okay, so when you look at how the C code is initializing the p next member, it is the address of node 1. So now, pictorially speaking, okay, instead of assuming node 1 is at a particular address, pictorially speaking, this is how people usually write it. Okay, they just use a pointer, use an arrow to indicate that the p next member, right here, the p next member of node 2 is pointing to the address of the entire node 1. Okay, so it's important to understand that this pointer is not really pointing to just n, it's pointing to the entire thing. Okay, so when we look at node 3, it's going to be very similar. Okay, so node 3 has v, has n, and v is 42, and then n, which is actually p next, is the address of node 2. So if we look at node 2 as one entire thing, then this is a pointer pointing to the beginning of that entire thing. So is this helping you guys to understand what is going on with a linked list? I certainly hope so. Right, back. Okay, the visual helps a lot. Okay, very good. Okay, so now that I figure out, I can do this, I just have to figure out, how to handle the heating issue, how not to make the processor, you know, uh, get up a little bit too hot. It's not going to kill itself. I mean, the thermal management is going to catch it before it blows up. Um, but still, if I can get it to run a little bit cooler, that would be nice. Yeah, so from here on, now that I know how to set this up so I can use the tablet mode while keeping my big large monitor on the other side, we can do things this way. Okay. We are almost running out of time, so today is one of those few days when I do not overrun the lecture time. But before I end the lecture, I just want to see if you guys have any questions. And I think it's probably a good time for me to release the next homework assignment, but this time I'll give you guys extra time to do. Okay. Um, Let me just go ahead and read assignment first, which is going to be your very last assignment. Oh, last. Oh, anytime, or at least. All right. Now to the last assignment. Calls. Okay, so this is the last one. And you can see it's worth even fewer points than the previous one. So the idea of doing this homework assignment is not so much for the points. It is really for just getting some hands-on experience, um, understand the concepts involved. Um, the quiz restriction, I'm gonna get rid of the access code. I'll give you guys a date. So we'll make it do 2 weeks. Okay, I'm just thinking, is that going to be in the final weeks already? What is the last day of lecture for this? I know somebody is tracking these things better than I do. Okay, nobody knows. Is the May 12th. So I don't know whether I want to make it May 12th or not, because if I make it May 12th, that means I won't have a chance to talk about the solution before the exam, and I want to be able to explain the solution before the final exam. So I'm gonna make this the 7th, so that I have a chance to talk about it. What is going to be on the final exam? All the stuff that we talk about after the second exam will be on the final exam. So, the use of structures, and then at some point recursive use, you know, structures and pointers and stuff like that. Those would be the items in the final exam. Make it due on May 10th. But the last lecture is going to be May 7th, so making the assignment due on May 10th is not going to help. Yeah, the 10th is a Sunday. All right, well, doesn't it doesn't bother me one way or another. I just cannot talk about the solution until the assignment is due. We'll want to 10th. Problem with that. Back to the 7th. Okay, I think it's better to, at least for the time being, make it the 7th. And if if a lot of people have problems and not, get it done by the 7th, then we'll talk about, maybe postponing it to the 10th. But the idea is, really need to get started with this one, like today, and work on it gradually. Okay, don't try to finish everything. So let me release it first, okay, and then I'll show you some code, for the code in this particular um, assignment. Okay, so you can see it is about the same, okay, except we have x and y instead of just one single value. And okay, I take it back. Yeah, take it back because the node actually has two pointers now. It has a left and a right. So in this case, it's actually creating, in the data structure class, what we know as a tree. Okay, the C code is here. Okay, the C code is called traverse. It is here. Okay, and the main code is going to be given. I have to finish this by giving you the main code. I think the main code is not. It is not. Okay, so I will give you the main code corresponding to this particular program, so you have some code to test with, and I will also give you the C code, and in a way that you can actually trace through the C code. That is really important, because if you can trace through the C code, then you know what the correct behavior of the program is, at least in C. So that will give you a clue of what the assembly code is supposed to do and how to debug it. Okay. So I will handle this as soon as possible, like right after I sign off from the live stream. I will give you the main file, okay, which is compilable in C. You can put it into code blocks or just a command line, compile it, go through the GDB, go through the debugger, then you can understand the behavior of that code. Okay. So do we have any additional issues before I sign off from live streaming? Because I'll still be, in the text channel. I'm just gonna turn off live streaming for now. Question? Right? So if there are no questions, I'm just gonna turn off live stream for now. And Top screen.